Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 4 of our unit Thermal Properties of Matter. So let's begin with today's class. Initially we are going to discuss about the specific heat capacity. So let's see what specific heat capacity is. We can say that the specific heat of a material is defined as the quantity of heat required by unit mass of the material to rise the temperature by 1 degree. That means the delta Q depends on two things. First, it depends on the mass of an object, it depends on the change in the temperature. So when I remove this proportionality symbol, I can have this a constant. This is what we call as the specific heat of the material of the body, and that could be represented as delta Q is equals to S into M into delta T. Many a time it is being represented by C. Many author write this. It's an MC delta T. Both are the same thing. Whether you use S or whether you use C, doesn't make any difference. But do you understand what the specific heat of the material or specific heat capacity is? Yes? Okay. So if I want the CGS unit and SI unit, it is something like this. This is MC delta T. While using C, this will be delta Q divided by M into delta T. So it's a delta Q by M delta T. Delta Q could be represented as calorie. Mass could be represented as gram, but it is divide by delta. It's a degree Celsius. I hope this is clear. Or I should write it for a SI unit. It's a joule per kg into Kelvin. Now, please understood and please remember this conversion. It's a 1 calorie per gram into degree Celsius. That would be equals to 4186 joule per kg into Kelvin. Approximately you can write this. It's a 4200 joule. That is divide by kg into Kelvin, because this is going to be used many a times. Please do remember this. Now let's work for the dimensional formula. This is delta Q is equals to M into C into delta T. This C could be represented as delta Q by M into delta T. Now this delta Q is the energy, and when I say it's an energy, that dimensionally it is kg meter square per second square. This is the mass. This represents kg. This delta K, it's a Kelvin. So this kg has gone, and I have been left with the meter square divided by second square into Kelvin. When I have said it's a meter square by second square into Kelvin, I should write this as an m0 L2 T minus 2 K to the power minus 1. So this is the dimensional formula of specific heat. It depends on the specific heat, depends on the nature of the substance, and it does not depend on the mass of the substance. So it does not depend on the mass actually. It depends on the nature of the substance. I hope this is clear. Is it clear? Is it clear? Are you sure? Now let's look certain quick questions. First, specific heat depends on the blank, and it does not depends on the mass of the substance. Yes, it depends on the nature of the substance. Second, what are the units and dimensions of specific gas constant? So, specific gas constant, that could be written as R is equals to capital R by M, where R is the universal gas constant and this small r is the specific gas constant. So it would be a joule per kg into Kelvin, or I should say it's an M0 L2 T minus 2 K minus 1. I hope this is clear. Is it clear? Is it? Are you sure? Yes, we are going to see this specific gas constant in more detail when we discuss the kinetic theory of gases, our next unit to this. Now let's discuss heat capacity. What is it? Let's have a look. We can also say it as a thermal capacity, or this is the heat capacity. We said that the quantity of heat required to rise the temperature of a body through 1 degree It is the quantity of heat required to rise the temperature of a body through 1 degree is called as the heat capacity of the body. And when I say that delta Q would be the quantity of heat given to the substance, and let's suppose rise in its temperature would be delta T, then this could be written as this heat capacity H, that could be equals to delta Q by delta T. Units of heat capacity will be equals to calorie per degree Celsius, because it's an H, that would be equals to delta Q by delta T, and this is temperature, so it's a calorie per Kelvin or calorie per degree Celsius. SI unit, it's a joule per Kelvin inverse, it's a joule per Kelvin. Dimensional formula, it's an M0L2 T minus 2 K minus 1. I hope this is clear. Is it clear? Is it clear what heat capacity is? Are you sure? Are you sure? So let's define it. So when some quantity of heat is given to the bodies of same mass but of different substances, please look at this, they should be same in mass but it would be a different substance. It is observed that the rise in temperature is different for different substances. So if it depends on the mass, it should be the same, but their masses are same, but even though their substances are different, and when the substances are different, then their heat capacities are different. So the heat capacity of a body depends on the nature of the substance, also on the mass of the body. Now do you understand this thing? Yes, the specific heat capacity only depends on the substance of the body and does not depend on the mass of the body. But heat capacity, it also depends on the mass of the body. Let's derive the relation between heat capacity and specific heat. So when a quantity of heat, which we call as a delta Q, is given to a body of mass m, let's suppose the rise in the temperature of the body will be delta T, then this H heat capacity could be written as delta Q by delta T, and specific heat could be written as delta Q by m delta T. So this is something like this, that delta Q is equals to ms delta T, and that's why H could be written as delta Q by delta T. It is ms delta T by delta T. This 2 has gone. So this H heat capacity is equals to mass times, it's a mass times of specific heat. It is something like this, heat capacity is mass times specific heat of a body. Do you understand this? Do you? That heat capacity is mass times the specific heat of a body. Do you understand this? Are you sure? Are you sure? Now let's move to the one more quantity that is to be known to get an idea of calorimetry. Let's first understand this. It's a water equivalent. It's a water equivalent of a body. So we can say that the water equivalent of a body is defined as the mass of water which absorbs the same quantity of heat for same rise in temperature. Or I can write like this, it is the mass of a water whose thermal capacity is equal to that of a given body. That is what we call as the water equivalent of that body. So formula wise, water equivalent of a given body could be represented as it's a heat capacity of given body divided by specific heat of water. Have you got this? Have you got this? We are going to use this in calorimetry. But up till now, do you understand each and everything? Are you sure? Let's look at quick questions. So heat capacity of a body depends on nature of the substance. Yes. Mass of the body. Yes. Volume. No. So both A and B. If I have been given the question that a specific heat of a body depends on If I have been asked this, specific heat of a body depends on, then I should write it depends on the nature of substance only. It depends on the nature of substance. I hope this is clear. Yes? Great. Let's work for the next question. It says the CGS unit of heat capacity. It's delta H, which is equals to delta Q divided by T, or I should say delta T. It's a calorie per degree Kelvin. This is the CGS unit of heat capacity. This is the SI unit. This is the SI unit of heat capacity. This is delta H is equals to delta Q by delta T. So this would be the correct answer. Next, the unit of water equivalent of a given body. It's gram. So basically water equivalent was, it's a heat capacity that I write as the delta Q by delta T divide by specific heat of a water, specific heat of a water. So when I say it's an specific heat of an water, that could be written as M as delta T, something like this. And when I solve this it would be the gram. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. Let's work for the next question. So is it clear up till now? Is it clear? Are you sure? Great. Now let's work for the next task. It's a change of state. So you might get confused that why we are learning all this, because let's have a guideline or outline of this. Basically we are working for the calorimetry, but to understand the calorimetry we need to have a little idea of certain terms. One is the specific heat, another term that is the heat capacity, another term that is latent heat, another term it's a water equivalent of body. So the situation is we are learning it one by one, and once we have been gone through this, then only we can reach to this, and then only we are capable enough to understand the calorimetry well. So we have done this latent heat we are going to discuss, and water equivalent of body has been discussed. So let's discuss a latent heat, but before we try to understand latent heat what is, first let's have a certain fundamental concept that why latent heat is required. So basically it is a change of state. When and when I look for any matter, it could be in three states. It could be in one of three states. Either it could be in solids, or it could be in liquid, or it could be in gases. When I need to change the state, this changes can occur when the exchange of the heat take place between the substance and its surrounding. So you can move from the solids to liquids or liquids to gases when certain amount of energy or certain specific amount of energy that is to be given to the substance from a certain different sources. So when this situation arises, this will happen and this task can be done. So what is latent heat? Let's have a look. It is the amount of heat. It is amount of heat absorbed or given out by unit mass. Sorry, by unit mass of a substance during the change of state. During the change of state, that is called as the latent heat. And this latent heat could be written as L is equals to Q by M, and its unit will be calorie per gram or joule per kg. So please do remember this value. Latent heat of fusion of ice, it's 80 calorie per gram, or if I convert this calorie per gram to the joule per kg, it's a 3.35 into 10 to the power 5. Please do remember this, that latent heat of fusion of ice, it means when you need to convert ice to water or water to ice, when you need to convert ice to water, you need to provide 80 calorie per gram, then you can convert 1 gram of ice by giving 80 calorie of energy to the 1 gram of water. It is something like this at the same temperature. I hope this is clear. Great. Now, latent heat of vaporization of water. Latent heat of vaporization of water, it's a 540 calorie per gram. Or if I convert this to joule per kg, this is 2.26 into 10 to the power 6 joule. When I say vaporization of water, that means I need to convert a water to steam, or let's say steam to water, something like this. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you understand this completely? Do you understand this? Are you sure? Are you sure? Any doubts up till now? Is there anything? No? Great. So, let's now understand that in the calorimetry, at this point of time, I don't know what calorimetry is and what it look like. But let's begin by something that in the calorimetry I have two tasks. One one is to change the temperature of substance, and another is to change the state of substance. So I will require this two tasks. First task to change the temperature of the substance. But while I'm going to change the temperature of the substance, its state will remain same. Its state is not going to change. And while I'm going to do this, it's to change the state of an substance. Temperature remains the same. It's a either or kind of task, that either I could do this or either I could do this. So, who will perform this task to change the temperature of the substance? It's a Q is equals to mc delta T. This is Q is equals to mc delta T. This function will perform the change in the temperature of the gas. While C of the water is 1 calorie per gram degree Celsius, and C of an ice, it's a 1 by 2, or remember it as a 0.5. It's a calorie per gram into degree Celsius. This is a degree Celsius. I hope this is clear. Please do remember this too. While if you want to perform the change in the state, who will perform this task? This task will be performed by Q is equals to ml. I hope you remember each term. Yes, this m is the mass of a substance, c is the specific heat capacity, and delta T is the change in temperature. You understood this. Now, here Q is equals to ml, where L is the latent heat. When you want to convert ice to water, it would be an 80 calorie per gram. And when you need to convert water to the steam, it would be a 540. It's a 540 calorie per gram. Please do remember this. We have discussed this in the previous slides too, but here it is the summarization sheet where you need to remember this too. It's a specific heat capacity for water and specific heat capacity for ice, as well as you need to remember latent heat for when you want to convert ice to water or when you want to convert water to steam, as well as you must substance each of the relation having their own role. Q is equals to mc delta T can work to change the temperature only. It cannot change the state. While Q is equals to ml can work for the change in state only. It cannot change the temperature. I hope this is clear. Is it clear? Is it clear? So now let's begin. Let's begin with the calorimetry. We have a primary idea that what could be done, but let's see it a completely in a theoretical manner. When I say calorimetry, I must say it's a branch of the science which deals with the measurement of heat. That is what we call as a calorimetry. A perfect calorimeter completely prevents heat from the flowing to its surroundings. That means it is not going to give any heat energy to the surrounding. Neither. So it is neither going to receive nor going to transmit any heat to the surrounding. I hope this is clear. Is it clear? Great. And we understood that at thermal equilibrium, all the materials are going to reach the same temperature, or I should say, at the same temperature, they will be in thermal equilibrium. I hope this is clear. Is it clear? So, how the calorimetry works, let's look. It's a principle of calorimetry. So, the situation will be if two bodies at two different temperatures are brought into the thermal contact, then what I assume is this is the formula: heat is lost by the hot body is equals to the heat is gained by the cold body, and this will keep on continue until they attain a thermal equilibrium. When I mean a thermal equilibrium, I mean that they both should be on the same temperature. So this is the only formula of calorimetry, that heat is lost by the hot body, that would be equals to heat gained by the cold body. This is the one and only formula for the calorimetry. I hope this is clear. Is it clear? Is it clear? So let's begin understanding of calorimetry and how it works and all that stuff. But before we proceed, we need to understand one very conceptual properties, that how the things will behave. Let's suppose we have one of the container, and in this container we have ice cubes. Let's understand that this are the ice cubes, and this is the container, and this container contains, let's say, 30 gram ice at minus 40 degrees Celsius. Now let's suppose understood that I have heated it up. I am heating it up. Shall I rewrite this? Yes, it's a 30 gram ice. Yes. So I am heating it up, and I am heating it up constantly, and plot I'm going to plot a graph for this situation, for the temperature versus energy, or I should say time, energy or time. So this source of energy will be completely there, and you can say that this is evacuated container. That means this ice cube has having only this source of energy, and other than this it could not receive, or not, it is not going to deliver an energy to that object. So let's understood what happened first. So ice is at minus 40 degrees Celsius, and this is a 30 gram ice is there, and it is going to be heat up. So what happens, that temperature of this ice will continue increasing from minus 40 to minus 30, minus 30 to minus 20, minus 20 to minus 10, and then 0. So let's say this is a minus of 40 degrees Celsius, and this is of 0 degrees Celsius. Who will perform this task? We don't know at this point of time. Let's write it as a Q1. Yes. Now you will observe that a time is being passed, energy is being supplied, but temperature is not going to change. It is certain a constant time. Who is going to perform this task? We don't know. It's a Q2, let's say. Now after certain time, again it start increasing its temperature, something like this. And when I measure this temperature using thermometer, it is 100 degrees Celsius. Who is going to perform this task? We don't know. It's a Q3, let's say. Next, again a certain time will arrive where temperature is constant and energy is being used, and again after some time it would be something like this. So who is going to perform this? It's a Q4. We don't know. Now look at this. The situation is, first look at this situation. Here the situation is that energy is being used from this to this, but temperature is not going to change. So the thing is, here the energy is being used to change the state at this point at 0 degrees Celsius. Your ice cubes was in the form of an ice at 0 degrees Celsius, while at this point it is at water. Again, temperature is same. So here it has been converted from ice to water. I hope this is clear. In this point it is at water at 100 degrees Celsius, and at this point it is at steam at at 100 degrees Celsius. I hope this is clear. Now, first thing, when I understand that this has been changed, how do I understand this, that this has been changed from ice to water? So the situation will be, look at this very carefully. I'm going to heat up this device. I'm going to heat up this device with this candle, and this is increasing its temperature minus 40 to minus 30, minus 30 to minus 20, minus 20 to minus 10, and minus 10 to 0. Let's say it is at right. So this is the amount of energy it is being used to convert this ice to a water. And at this position you are having a 30 gram of water. That means, until, please understood and please listen this very carefully, until this whole mass, that means the mass of 30 gram ice converted to 30 gram of water, it is not going to change its temperature. I hope this is clear. So if you look at the any instant, any this particular instant, its temperature is 0 degrees Celsius, because it is the time span where total mass of the ice is going to be converted. If you are not having a sufficient amount of energy, then the situation will be the mixture, because it is quite possible that certain mass has been melted and certain mass of the ice has been melted and it is now a water, but certain other mass is not going to be melted, something like this. It is quite possible. So in this situation temperature remains the 0 degrees Celsius. Again, once this 30 gram ice, which was here, it is 30 gram ice, once it is converted to 30 gram water here, it is going to change the temperature from 0 degrees Celsius to 100 degrees Celsius. Have you got this? Have you got this? So it is the situation where here it's a water at 100 degrees Celsius, or I should say it's a 30 gram water at 100 degrees Celsius. Again, this is the time, or this is the energy that has been provided to change from water to steam, but it is not going to change its state until this 30 gram water is converted to 30 gram steam at 100 degrees Celsius. I hope this is clear. So what you need to understand is that who will perform this Q1, who will perform this Q3? It is the ms delta t or mc delta t who will perform this. Who will perform this Q2 and Q4? It is the ml. But I'm just talking about that. Let's This could be confusing. This could be confusing. Let's delete it from here and write it down on here. This q1 would be ms delta t. This q2 would be m into l. This q3 would be ms delta t, and this q4 would be equals to m into l. While I'm writing here it's an ms delta t, this s would be one half over here because it is in the form of a ice. This L would be equals to 80 calorie per gram. This S would be a 1 over here because it is the phase of a water, and this L, it's a 540 calorie per gram. I hope this is clear. Mass you understand, whatever that has been given. I hope this is clear. Is it clear? Are you sure? Any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Correct. So now what we are going to do is we will understand the calorimetry from the example point of view only. Yes, it is the best approach to understand the calorimetry. So let's have a look. Suppose the situation is that this is the container which we call a calorimeter, and this container is having certain ice cube in it, and this is having a water as well. Let's suppose this is having a 30 gram of ice at minus 40 degrees Celsius, and this is having a 20 gram of water, 20 gram of water at 50 degrees Celsius. So the question is find out temperature and composition of mixture. Yes, it's a closed container which we call as in calorimeter, sorry. When they say composition of mixture, they mean after some time what amount of water has been left, what amount of ice has been left, and everything. So this is basically a calorimeter. This container is a calorimeter, and as we have discussed previously that calorimeter is a device which does not allow heat to be transferred from calorimeter to the surrounding. Even it is not going to accept any heat from the surrounding to the calorimeter. Yes, so now what will be happen? Basically these two things have been mixed in this mixture. It's a water and it's an ice. So according to the principle of the body, heat gained by by cold body is equals to heat lost by hot body. So it is total amount of heat gained is equals to total amount of heat lost. It is the simple principle. While in my case it is the heat gained by ice would be equals to heat lost by water. I hope this is clear. So always do remember this thing. How will you decide that from where to where heat will flow? Answer of this question can be given by the temperature of an object that you have mixed up here. Yes, higher the temperature, it is having a capability to deliver the heat. It is having a capability to lose the heat. Lower the temperature, it would be having an capability to gain the heat. I hope this is clear. So what I'm going to use the strategy is I'm going to use the strategy is that please do remember this. Always convert every objects to 0 degrees Celsius water. Always do this. Yes, when I say every object or every substance, basically we have, when the questions has been asked, we have only three things. We have ice, we have water, or we have a steam at max. We do not find anything other than this. In most cases of calorimeter. Yes, so first do this and then you will get an idea that how other different category of questions can be done. So first look at this, observe this. Always do this, that always convert all the objects always convert all the objects to the 0 degree Celsius of water. So how will I convert this? First I need to calculate that heat lost by water. So mass of the water, it's a please do write this, it's a 20 gram water at 50 degrees Celsius, and Also write this, it's a 30 gram ice at minus 40 degrees Celsius. So mass of the water in our case it's a 20 gram, and temperature of the water currently it is at 50 degrees Celsius. So to reach this to the 0 degree, what it needs to do is, it is at 50 degrees Celsius and it is already water. So it is already in a water and it needs to decrease its temperature. So who will work? Q is equals to mc delta T or Q is equals to ml? Who will work for me? Yes, you are correct. That Q is equals to mc delta T can work. This M, it's a 20 gram. C would be the one. Delta T, it's a 50 degrees Celsius because it will reach from 50 to 0. So it's a 50 minus of 0. It's a 50. So it's a 20 into 50, which is equals to 1000 calorie. So this is heat loss by the water, or this could be written as Q available, that this much amount of energy I can possess. Next, I should say it's a heat that is gained by the ice, or in fact in reality this is heat required by ice. It's a heat required by ice to reach at 0 degree Celsius water. So what is the constituents, or what are the data of the ice? It's a mass of the ice, it's a 30 gram, and temperature of the ice, it's 40 degrees Celsius. I mean it's a minus of 40 degrees Celsius. And specific heat capacity of ice, it's a 1 by 2 units. So first what you need to do is convert this minus 40, convert this minus 40 to 0 degrees Celsius. This is first task. Minus 40 degrees Celsius ice to 0 degrees Celsius. In both the states it is ice only. So when the state is same but temperature is going to change, it's from minus 40 to 0. So this will be given as Q is equals to mc delta T. Mass is 30, C is half. This is a 40. It's a minus of 40 to 0. It would be a 40. This is 220s. This is 30 into 20. This is 600 calorie is required to perform this task from minus 40 to 0. And this is just the one task. But here it's a 0 degrees Celsius ice. What I want 0 degrees Celsius water. So it's a second task. A second task, it is at 0 degrees Celsius ice. You need to convert this at a 0 degrees Celsius, but now it should be in water. So look at this. Temperature remains the same, but state is going to change. And when I say it's a state is going to change, I mean it's a Q2 is equals to M into L will play its role. It's a mass, that is what we understood. It's a 30 L, it's an 80 calorie per gram. This is 2400 calorie. So the total requirement to do this, that means total requirement by a 30 gram ice cubes from minus 40 degrees Celsius to reach at the 0 degree Celsius water would be this 600 plus 2400, which is equals to 3000 calorie. This is the requirement. Now the situation is, what amount of energy water can give? It's a Q available, that is 1000 calorie, and this is Q required, this is Q required by an ice. It's a 600 plus 2400 calorie. So what I understand is this 600 calorie, this Q1 has been used, this Q1 has been used to minus 40 to 0, and this 2400 has been used from 0 degrees Celsius to 0 degrees Celsius. You now understand this, that 0 to 0, that means ml has been play its role. So what I understood is from this 1000 calorie only this task can be performed, and this is not going to be completed. Yes, it will start beginning, it will perform its task up to certain level, but this cannot melt all the masses. So if it can convert this. It can convert this, but it cannot convert all its ice cubes. So it is something situation, something like this. Look at this graph. Yes, it is from this phase to this phase somewhere. Yes, this minus 40 to 0 has been achieved, but 0 to 0 cannot be achieved. So from this point, I understood that temperature of mixture is at 0 degree Celsius. That is for sure. I hope this is clear. Is it clear? It's a temperature of mixture is at 0 degree Celsius. It is for sure. Why? Because it cannot convert the complete mass. So, so is it clear? Now let's work for the second question. That what should be the constituents of the situation? So from this 1000 calorie, 600 calorie and 400 calorie I have been left with. So this 600 calorie is going to be used as a Q1 to convert minus 40 to 0. Now I have been left with the only 400, and I understand that this from 400 this 2400 calorie task cannot be performed. So what I understand is total mass cannot be melted. Total ice cubes cannot be melted. But the question is, forget about the total mass. Just let me know that what amount of ice you can melt. So it's an amount of ice can be melted, can be calculated as Q available is equals to M into L. While I say Q available, don't make a mistake to use 1000 calorie, because from this 1000 you have used this 600. You have been left with only 400. So it's a 400 calorie. Mass you don't know. L it's an 80. When you use this, this M can be given. It's a 5 gram of ice can be converted. 5 gram of ice can be converted. When I say this 5 gram of ice can be converted, so now the situation is, that initial, this is, let's write down the initial composition as well. The mass of the water was 20 gram. Temperature of the water was at 50 degrees Celsius. Mass of the ice was at 30 gram, and temperature of ice was at minus of 40 degrees Celsius. Now let's look at the final situation. The finally it is having mass of a water that is equals to 20 gram plus this 5 gram. This is the mass which has been melted from the ice to the water, but temperature of the water it is at 0 degree Celsius. Mass of the ice is, it's a 30 gram. Initially it was there, minus of this 5 gram. Yes, because it has been melted. And the temperature of the ice cube is 0 degree Celsius. So basically it's a temperature of the mixture. This is temperature of mixture, which is at 0 degree Celsius. Yes, and now it cannot move proceed because all the available energy has been used. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? So are you ready to perform the same thing one more time? Are you sure? Are you sure? Can we do this? Can we? Can we do this? Are you sure? Great. So let's do this question one more time by certain modification. So the question says that in the previous question, if Mass of water is 70 gram. Find find temperature of the mixture and constituents of mixture. So how will you do this? How will you do this? You have data written on your book that the situation would be, it is something like this, that this is calorimeter, and in this ice cubes are there, and the ice cubes are of 30 gram, which is at minus of 40 degrees Celsius. This is ice, and with it even a water is there. Now our water is of 70 gram, which is at 50 degrees Celsius. This is talking about the water, and this has been completely closed container. Basically it's a calorimeter. So now again, what you need to do, now you understand that heat gain is equals to heat lost. First calculate the Q available. That means the water will donate the heat and ice will accept the heat. So what amount of heat can be donated? What amount of heat can be donated by the water? Let's have a look. First, it's a Q is equals to mc delta T. This is 70 into 1 into 50. This is 3500 calorie. This is Q available. That means this much amount of energy, this much amount of energy can be available by the water. Now let's look at this. What amount of ice, what amounts of energy can ice require? So first it will require to switch from minus 40 to 0. It's an mc delta T. The mass is the 30 gram, C is the half, delta T it's a 40. So this is 30 into 20, this is 600 calorie. This is Q1. This is Q2, which will be M into L. This is 0 degrees Celsius to 0 degrees Celsius. Yes, it's an M into L. This is 30 into 80, which will be 2400 calorie. So the Q total requirement, its Q total requirement will be equals to, it's a 600 plus 2400. This is equals to 3000 calorie. If this energy is available, let's say if this energy available, then I can say this 30 gram ice will be converted to 30 gram water at 0 degrees Celsius if 3000 calories available. Now what is available amount of energy? This Q available is, it's a 3500 calorie. Look at this, it's a Q available, it's a 3500 calorie. I hope you understand this. So now tell me, from this 3500 calorie, can we have a work of 3000 calorie? Answer would be definitely yes. So what I supposed to do is that divide this 3500 calorie into two part. One of the part is 3000 calorie that will require to do this task. And when I say this task, that this first task, this second task. First task, from minus 40 degrees Celsius to 0 degrees Celsius in a form of ice, and the second task, it is from 0 degrees Celsius in ice to 0 degrees Celsius in water. So this will require 3000 calorie, but I have been left with more 500 calorie. What I will do with this? What should I do with this? Yes, it's a 500 calorie available. Still even though we are going to do this, still I am having the 500 calorie. So this 500 calorie will be used to increase the temperature of the mixture. How? Let's look. So the increase in the temperature, increase in the temperature of mixture, that is Q is equals to M total into C into delta T. So the total mass would be, I am having the 30 gram of ice and I am having a 70 gram of water. So it's a 30 plus 70 into 1 into delta T. What amount of energy I have been left? I have been left with the 500 calorie. So it's a 500 is equals to 30 plus 70, 100 into 1 into delta T. From this it's a delta T which is equals to 500 by 100, which is equals to 5 degrees Celsius. So now we got every answer. First, temperature of mixture, it's a 5 degrees Celsius. A mixture contains 30 gram plus 70 gram equals to 100 gram of water. This is the final constituents of the calorimeter. I hope this is clear. Is it clear? So now do you understand completely what is to be done if I have been short of energy, and what is to be done? What is to be done if I am having an excess amount of energy? Are you sure? Can you do this? Can you? Can it be done? Can it be done? Are you sure? Great. So, ready for the next question? Are you ready? Great. Shall I mix the steam with it? Shall I? Let's have a look. Let's suppose this is calorimeter, and in this calorimeter we have ice cubes, something like this. These are the ice cubes, and this ice is mass of ice, it's a 20 gram, and which is, let's say it's a minus of 30 degrees Celsius. It is having water as well. This is water. The mass of the water is, let's say it's 30 gram of water, which is at temperature of 50 degrees Celsius. It is having certain steam too. That this is the steam, and this mass of the steam, it's a 5 gram, and the temperature, it's an 100 degrees Celsius. I hope this is clear. This is the steam. So the question remains the same. Find out temperature and composition of mixture. Find out the temperature and composition of mixture. How will I do this? So again, as per our strategy, convert everything to the 0 degree Celsius water. So let's first begin with the steam. That steam is at already 100 degrees Celsius, and it is in a state of ready to convert because it is already at 100 degrees Celsius. So what it will provide, it's a Q is equals to ml. This will make my steam to 100 degrees Celsius to 100 degrees Celsius. While I say 100 to 100, this is steam, this is water. So this is Q is equals to ml, and this will be a 5 gram of steam multiplied by 540. It's a 540 calorie per gram. So it's a 2500 plus 200, it's a 2700 calorie amount of energy. But this is now, after this amount of energy, it can be at 100 degrees Celsius, but water, what I want at 0 degree Celsius water. So this is Q1, this is Q2, that is MC delta T. While I say it's an MC delta T, it would be 5 gram of steam multiplied by 1 into 100. This is equals to 500 calorie. So Q available by steam only, by steam only. I have not touched the water yet. That Q available by water only, steam only, sorry, it's a 2700 plus 500, it's a 3200 calorie. This much amount of energy, this much amount of energy by the steam. So this is Q available by steam. I hope this is clear. Now what next? I need to write down available energy by the water. So Q is equals to mc delta T. This is for 50 degrees Celsius to 0 degrees Celsius. Here it was water, even here it is at water. So mass, its a mass is the 30 gram, C is the 1, delta T it's a 50. So this is 1500 calorie. So now Q total available by water plus steam, Q total, that is this 3200 by the steam plus 1500 by the water. So total amount of energy it's a 4700 calorie. This is Q total that is available to do the task. I hope this is clear. Now what I need to do, I need to take a consideration of the ice cubes, that what ice will require and what amount of energy is required. So first task, it's a Q1 that is equals to mc delta T. This will convert for me minus 32 0 degrees Celsius, but here it is ice, even here it is ice. So this is equals to mass, it's a 20 gram, into C it's an half, into delta T this is 30. So this 20 2s are 10 and this is 30 10s are, this is 300 calorie. This much amount, this much amount of energy is required to minus 30 to 0. And then Q2, it's an m into L. This Q2, this is equals to m into L. This will be 20 gram of ice cubes are there, multiplied by L, it's an 80. This is equals to 1600 calorie. So Q required, total Q required by the ice, it's a 600 plus 300, this is equals to 1900 calorie. I hope this is clear. Do I have available? Yes, definitely, much greater than what required. So what I need to do is, let's understood that this Q available is 4700 calorie. Divide this into two parts. One, it's one, the requirement of this is equals to 1900 calorie. So this is 1900, and the remaining energy, what amount is remaining? It's a 2800. This much energy has been remained, so this is going to used to convert ice from minus 30 degrees Celsius to 0 degrees Celsius, but now it is in water. And what amount of energy I have been left with? I have been left with the 2800. So what this energy will do, this energy will this energy will make to increase the temperature of mixture. So let's see what happens. So this Q is equals to m total into C into delta T. What is amount of energy available? It's a 2800 calorie. M total, what is it? It is a 20 gram of ice plus 30 gram of water plus 5 gram of steam. This all are at 0 degree Celsius water. I hope this is clear. Is it clear? So we have this combination, it's a 20 gram of ice plus 30 gram of water. This is ice and this was steam, multiplied by 1 into delta T. So this 2800 is equals to 20 plus 30, 50, 50 plus 5, it's a 55 into 1 into delta T. So the situation would be equals to 2800 divided by 55, which would be which would be approximately 50.90, or you can say approximately 51 degrees Celsius. This is the temperature. This is the temperature of the mixture. It's a 51 degrees Celsius, and it contains 20 plus 30, 50, 50 plus 5. It contains a 55 gram of water. It is the last situation of the container. I hope this is clear. Is it clear? Is it clear? Are you sure? So can you do this? Can you do this kind of questions? Are you sure? Are you sure? So this is the first category of question. These are the first category of questions that has been asked based on the calorimetry. Now let's look at a certain other category of questions too. Let's suppose understood that this is the box, and in which an ice has been there at 0 degree Celsius. It is an m amount of my ice, a very large amount of ice has been there, and let's say this is bullet. Mass of the bullet, it's a 40 gram, and it is moving in this direction with a velocity of 800 meter per second. If 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 this bullet has been reached to this, and it came to rest over here, the question says that find out find out amount of ice that has been melted. So this is the requirement. Ice is there, and it is at 0 degree Celsius. So it is ready to convert, something like that. Yes. uh, Now in this case the question is who will provide me the energy. So what I understand and what you also understand is it is the kinetic energy. It is the kinetic energy that will provide me the required energy, because initially it is moving with 800 meter per second and it came to rest over here. That means total kinetic energy has been used to melt this mass. So it's an Q available is equals to half into m into v square. What I get it. So it's a Q is equals to half mv square. Let's calculate it. It's an half multiplied by m. It's a 40 gram. So convert this to kg. It's 1,000. V square, this is 8 into 8 into 10 to the power 4. It's a 800. So basically the situation is this is 1, 2 and 3. Even 3 power has been lost and only 1 power has been remained. So again it's a 2 into 4. So I have been left with this is 40 into 10, which is equals to 400 multiplied by 4 8s are 32. So basically it's a 32 multiplied by 400. And if I do this, it's a 32 into 400. It is a 12800. But this is joule. This is joule. Please be very careful while using it. It's a joule. So when I need to convert, if I want to use L as an 80 calorie, then I need to convert that to joule, or I need to convert this joule to calorie. Yes, but this is SI system. Even I'm going to use this. Then this Q is equals to M into L. This Q available is in joule. So this is equals to 18,000, sorry, 12,800. This is 12800. It's equals to M into L. This L is 80 calorie per gram. We understand that L of ice, it's an 80 calorie per gram. Now how to convert this to kg? It's a, sorry, joule per kg. Have you remembered this? Have you remember once we have been done this, we have written that two values, that please do remember this. Have you got this? Yes, look at this. It's a 3.35 into 10 to the power 5 joule per kg. I have done the simply the same thing, converted the calorie to the joule and gram to the kg. Yes, so please do remember this thing. It's a 3.35 into 10 to the power 5. So use this. It's a 3.35 into 10 to the power 5. This is equals to 3.35 into 10 to the power 5. So this is basically 128 into 10 to the power 2 is equals to m into 335 divide by 100 into 10 to the power 5. So this has been 2 power has been gone, or I should write this as a 10 to the power 5 to the 10 to the power 2 into 10 to the power 3. So this 100 and this 100 has gone. So I have been left with m, which is equals to 128 into 10 square divide by 335 into 10 to the power 3. So this is equals to 128 divided by 335 into 1 by 10. I hope this is clear. So, so this is only the 128 divided by 335, which is equals to 0.38 divide by 10. So it's a 0.03 kg of ice has been melted. I hope this is clear. Is it clear? Is it clear? So can you do this kind of questions? Can you do this kind of questions? Are you sure? Are you sure? Great. So let's wind it up the session over here. This was the concept of the calorimetry, and to understand the calorimetry we have used every definitions that can be used to understand the calorimetry. So we have begin with the definitions, and then we have covered the calorimetry. It is a very important topic. If you see the previous year questions, then you will observe that no paper can be completed, no paper can be completed without asking a question of calorimetry, whether it could be of JEE mains, or whether it could be a NEET. So please revise this and make a practice a lot this kind of questions, because this is going to be asked for sure. This will help us to crack our examinations and save the time too. Thank you. Have a good day. Take care. Bye bye.